Okay, so here's where we were last time. We were talking about Green's theorem. Real quick, I don't want to go through all of the sort of development again, but I want to remind you what the big points were. We had to make a precise definition of what we meant by the orientation of a boundary. And again, the word boundary going forward in chapter 6 and 7 means an oriented thing. And specifically, this is the rule, regions on your left, etc. Okay. All right, the next big contributing idea is this idea of accumulation. And, just for the record, I mean, there's a lot of things that do have the feature of accumulation, but not everything does, and it absolutely cannot be taken for granted. So perimeter, for example, not an accumulating quantity, right? The perimeter of D1 plus the perimeter of D2, clearly not the same as the perimeter of D itself. It is nice, though, when something actually has this feature of accumulation. And arguably the biggest point about Green's theorem is that boundary circulation, this quantity called boundary circulation. If you give me a two-dimensional region, I can say, well, let's look at the boundary and compute the circulation of a given vector field on that boundary. That quantity, boundary circulation, is an accumulating quantity, which is super weird because it doesn't seem like it ought to be. It seems like it's a silly math game, right? But it is. Boundary circulation accumulates. In some sense, what it really comes down to is this extra piece, which when we were talking about perimeter was a problem. But here we're going one direction on one side, we're going the opposite direction on the other side. And yeah, it's there twice, but they cancel. And so it's like it's not there at all. Okay, beautiful fact. So boundary circulation accumulates. So I think it's a valuable idea to think about boundary circulation, even though it seems like it's something that's kind of computed on the boundary, to think of it as like a stuff-like thing, right? Think of it as being physical, something concrete. And that even though you compute it on the boundary, you can think of it as actually accumulating over the interior. And that it's like it's stuff distributed throughout the interior. And that the boundary circulation you compute, you're actually adding up boundary circulations of all the little pieces sort of in between. Okay, well, that idea noted, then we can make sense out of what we mean by a density, since we can talk about boundary circulation as accumulating over the interior, right? That there's a bunch of little pieces of boundary circulation all over the interior. I can look at individual ones and say, for example, let's see here, let me do this with the pencil. I can talk about the boundary circulation on this little square. Right, now that boundary circulation is contributing to a whole of boundary circulation around some larger region, but that amount of boundary circulation per unit area gives a notion of density. And in the same way that the accumulating quantity of mass per unit area gives you mass density, likewise, circulation per unit area, I'm going to think of that as circulation density. Here's well, I guess we got a little bit further than this last time, but there is this weird fact that circulation per unit area, circulation density goes by many names. You can call it Green's operator because it's the operator involved in Green's theorem that we're about to write down. I like to abbreviate that for convenience. So GRN, I think I may have made that up. I don't know. But other common notations are ROT for rotation. If you think about it, why do they call it rotation? Well, because it is measuring the extent to which the fluid is kind of rotating around, right? Circulating, literally. So very reasonable terminology. And then curl. I have my quibbles with this term. Curl is primarily to designate something that happens in 3 dimensions. That's very closely related to this, yes, but it is also different in some important ways, some qualitative ways. So anyway, you can call it curl. Our book, I believe, calls it curl in more than one place. It's not my personal preference, but anyway. And then there's this notation over here that I guess it's fine because it's in the book, but I don't see the advantages of it. It is not particularly elegant. It's not particularly convenient to write down, and it's also just a little bit wrong. So anyway, whatever. Okay, so circulation density. And how do we compute this mysterious quantity? Formula dq dx minus dp dy. Okay, so with all of this set, we can remind ourselves of where Green's theorem came from. Green's theorem is just observation that this quantity called circulation, thinking of it as a quantity, I think it's nice to think of it as a quantity, give it a name and a notation, accumulates, as we discussed. This is computed on the boundary, yeah, whatever. This is something that we should think of as actually accumulating over the interior, just like mass does. And when you've got something that accumulates like that, and therefore you can talk about the amount of it that's happening in particular places, reasonable to talk about the corresponding density, which of course we did above, right? And we've got this, this notion of density here, Green's operator, rotation, circulation, whatever you want to call it, right? And as a result, we've got ourselves a theorem. 2 seconds, I see. Let me just wrap up the punchline here is that Green's theorem says that this line integral circulation can be computed with this double integral of Green's operator. Yes?
I was just wondering why those words are drawn with arrows to the equal signs.
Oh, I'm just making the observation of what each one of these equal signs, each one of these steps in the process is doing. So when I say circulation can be computed as a double integral of, like that, I'm just observing that this circulation has this feature called accumulation. So I can do this because circulation is a stuff-like, mass-like kind of thing that adds up like that. So you cannot do this with perimeter, right? You cannot say perimeter is a double integral of dp. It doesn't make any sense at all. It's complete nonsense. So yeah, so that's right. And then how did I take this step here? I make this step by invoking that there is the associated notion of density. Yeah, cool. All right, so there you go, Green's theorem. And let's see, I think that's where we left off last time, if I remember correctly. So let's proceed. I'm going to show you all an example. And I guess I'll zoom back in so we can see better. So suppose you want to compute this line integral. And that's a line integral over a given curve of a given vector field. Now, I want to take a quick moment to recognize, you'll notice nothing about the statement of this question says, use Green's theorem, right? So this is just, hey, let's compute this line. So you could, there's nothing stopping you from saying, well, maybe I'll just compute this plug and chug, I'll parameterize this. I know how to parameterize the unit circle, and then we do the usual pullback to compute a vector line integral and plug and chug, turn the crank. Now, just because we could doesn't mean it's a good idea. And if you try to think forward, okay, think a couple of moves ahead, what would happen if you did this, right? Well, if you parameterize the unit circle, you're going to have sines and cosines. X and Y are going to be sines and cosines. That means that you've got trig, trig, trig of trig, and more trig. Again, there's not that you can't do it, I guess, but this is not an appealing prospect, right? So doesn't look like a good option. Okay. Okay, so what we're going to do is we're going to try to take this different approach. We have this other tool for computing line integrals. And let's see if we can use that. Now, there is a catch. Green's theorem, you'll notice, does not say, oh, you can compute any line integral with the following formula. Green's theorem, as stated, as we're looking at it right here, indicates very clearly that this only works for some line integrals, and it does so by the fact that it says right here, your curve's got to be a boundary, right there in the statement of the theorem, right? This Green's theorem does not allow you to just compute random line integrals, only boundaries. Okay, so let's keep that in mind. Is our clockwise oriented unit circle a boundary? And well, technically, no, it's oriented the wrong way. Again, keep in mind, this word boundary is a loaded word. It's very rigid, very, very finicky, very delicate. This is not a boundary, it's going the wrong way. So it's tempting to kind of throw in the towel and say we can't use Green's theorem. But here's the good thing. What I can do is I can relate the curve that I'm interested in, the clockwise oriented unit circle. I can relate it with the counterclockwise oriented unit circle. Recall this notation here, this little superscript minus sign is just saying go the opposite way. You know, same curve, other direction. And this counterclockwise oriented is a boundary. It's literally the boundary of this ball in between there. So what we're going to do is we're going to compute the green line integral by relating it to the blue line integral, and the blue one's the one we're actually going to compute. Okay, does everybody see what happened there? Okay. Right. Okay. So let me, yeah. Okay. So, colors. C is the opposite orientation of C minus. So we get a minus sign in that connection there. C minus is literally a boundary. So let's denote that, right? I mean, that the fact that it's a boundary is very important to how we're going to compute it. So I want to indicate explicitly C minus is that boundary. And having made that note, now I see I've got exactly what Green's theorem addresses. I have here a line integral, vector line integral around a boundary. And because it is a line integral around a boundary as required, I can say, okay, cool, Green's theorem, double integral of Green's operator. And bam. And of course, now don't forget this minus sign comes along for the ride, right? That minus sign doesn't just disappear, right? But that's, we've got to maintain that. Okay. All right, so did this help us? Well, we're going to have to compute Green's operator, right? I'm going to have to take this vector field and plug in and see what Green's operator is. Remember the formula for Green's operator? We've got that up here. It's here it is, dq dx minus dp dy. By the way, again, reminder, you're welcome to use any of these notations that you like. Oh gosh, begrudgingly, I guess you, but I encourage very strongly, pick one of these three right here. And dq dx minus dp dy. So computing that for this vector field, let's see, we need the x partial of that, 3, minus the y partial of that, 1. And so really easy calculation for Green's operator, it's 2. Double integral is trivial because it's a known domain, right? This is a unit disk, and it's all over but the shouting. And did I miss a minus sign? I forgot my minus sign. Okay, shame on me. Look at that. This is me teaching by counterexample. There is a minus sign in there, not to be forgotten. So I need to insert that right now. and I will get these notes fixed. Hopefully before lunch. Okay, how are we doing? Everybody see what I did wrong and how to fix it? Okay. Alrighty, good deal. Here's another example. This one's a little weird, but I like weird examples because the more sort of curveballs I show you how to hit, the more curveballs you'll be able to hit on exams. So we have a curve here that is made up of line segments starting at the origin and then going to 2, 2, and then down to 2, 0, and then up to 0, 2, and then back down to the origin. So there's our curve described there. And is this curve a boundary? Well, no, not really quite, right? But here's the thing. I can reinterpret this curve as being, this is going to seem like cheating, but this is fine. I'm going to reinterpret this curve as the sum of those 3 blue segments plus the sum of these 3 green segments. And the sum of the 3 blue segments, you will notice, is a boundary. It's literally the boundary, orientation and all, of D1. Yeah. And the green area, okay, well, not technically a boundary as it's written, right? Because it's going the wrong way. It's going clockwise to the count, however you want to say it. Region's on my right. But other than the orientation being wrong, it's exactly the boundary of D2. And so I can say, okay, well, D2, the green curve, it's not exactly the boundary, but it is the opposite orientation of the boundary. So that's the little orientation switch there. How y'all feel about that? There's a neat trick to, again, look at your curve and feel free to, reconceive it as needed. But here's where we go from there then. The curve being boundary of D1 plus the opposite of the boundary of D2. Right, break it up into 2 separate pieces like that. And then we'll just deal with each one separately. This minus sign means opposite orientation. So that means we're going to get a minus sign on the value of the integral. No problem. Green's theorem applied to that region on the left. And then separately, now don't forget that minus sign that's got to come along for the ride, but then I can also apply Green's theorem to this region on the right. Is everybody with me? Is that good? And again, it comes down to, well, let's compute Green's operator and proceed. So let's see, coming back up to the vector field here, dq dx is 5. Now I have to say minus dp dy, so minus the y partial of this, so minus -4. And so Green's operator is 5 minus -4. Green's operator is 9. Everybody follow me on that? And so again, worked out really nicely. Again, we have these are easy domains. They're familiar triangles, not hard to compute their areas. And not that we have to, we can even more easily argue these 2 triangles have the same area. And so we're subtracting something from itself. And so we get 0. Yes.
Is there like a way to make a symmetry argument here?
That's a great question. It's tricky. When you're talking about vector line integrals, it's tempting to say, well, look, there's a symmetry argument for single variable integrals and double integrals and triple integrals. Why not other kinds of integrals? It turns out when you have oriented integrals like vector line integrals, there is a symmetry theorem, but it's real tricky and it's not what you think it is. And it's not a state. It's not about is the integrand odd? There's a different requirement. And yeah, it's I'm going to say it's not worth it For whatever it's worth, in my own textbook, I actually have a series of exercises. There's like 5 or 6 exercises that build up to, I forgot how I did it. But anyway, the series of exercises, the punchline of which was for students to sort of discover the symmetry theorems for vector line integrals. And the reason I put it in there was A, it's mathematical weightlifting. It's good exercise in thinking about hard ideas. But B, I wanted students to have the up close and personal and viscerally experienced realization that this is not worth it. So I would say, yeah, don't think symmetry when you're looking at vector line integrals. Yeah, but it's a great question. Yeah. Okay. All righty. Okay, here's another neat thing you can do with Green's theorem. This is a real tricky little observation, very clever. Ultimately, it comes down to what would happen if Green's operator were 1. And I think this is a natural question to ask if you think about it, because you're like, well, I am, after all, doing a double integral of this thing. I love it when my integrand is 1 when I'm doing a double integral, because if my integrand's 1, it's just area. Area is a natural thing. I love it being able to connect natural ideas, things that you know are relevant or possibly even convenient, connecting it to other things. So wouldn't it be neat if we could come with a vector field for which Green's operator is 1? And well, it turns out this is not at all hard to do. In fact, there's lots of operators for, lots of vector fields for which Green's operator is 1. And 0, x, I think, is the easiest one to write down. Not hard to persuade yourself, right? dq dx minus dp dy, you get 1. There are many, many others. And I'm just going to use 0, x because it's the easiest one, and I don't see that the others have any particular advantages over, so I'm going to go with the easiest one. Okay, so what we've got then is that a line integral around the boundary of a region will compute the area if you use the right vector field, right? And of course, the key idea is you've got to use this vector field, 0, x. Or one of the many others which you could choose from, and I don't see why. Let's just use this one. How are we doing? Is everybody on board so far? Okay. So I'm also going to use this other notation that I've already kind of badmouth a little bit, because notice writing it as a coordinate line integral, just a little bit more compact in this case. And usually it's quite the opposite, right? Usually it's plunkier to write it that way, but it's very pithy and compact to write integral x dy, which of course just means that, right? But I'm going to use this for convenience. Okay, so a coordinate line integral computes area. Fine. So what does that allow me to do? Well, how do I compute integral x dy? On a boundary curve, you parameterize and plug and chug. But it turns out if you focus your attention, instead of on an entire boundary, if you just look at a straight line segment, it's really easy to compute integral x dy. This specific integral x dy on a line segment is the average value of x, just average the x coordinates of the endpoints, times the change in y as you move along that line segment. So y2 minus y1. Just a snap, nothing to it. Now, why is this true? Plug and chug. And I think this is a healthy exercise. I encourage everybody to do this. Y'all know how to parameterize a straight line. Straight line from one point to another. Explicitly brute force write down that parameterization. Plug that parameterization into this coordinate line integral and punch it up. It's really not that, there's no tricky curves on this. It's just literally plug in the parameterization and take a deep breath and plow forward, and you will get this as your result as it happens. So again, healthy exercise. I hope everybody will give that a try. So between the two of these facts, we've actually got a nice tool. If you want to compute an area, we see that we have to compute integral x dy around the boundary. Well, the boundary might be made up of a bunch of line segments on each of which the work is easy. And altogether, then you can compute the areas of things. And so here's I think a pretty dramatic example. Let's look at this monstrosity over here, right? How would I compute the area of that thing? Well, you could break this up into a bunch of little triangles. They're mostly not right triangles. That's going to be a pain. You could view this as kind of overlapping simpler triangles, or maybe simpler trapezoids or something like that. But that's going to get pretty messy because of all the zigzaggy that's going on over there. And it's going to be super easy to get confused. Wait, these overlap. I've got three things overlapping. How many should this one be, minus or plus? That gets really confusing really fast. But it's very, very straightforward to do this calculation we just talked about, because each one of these line segments, let's take that one, for example, each one is easy to work with. So let's take this, again, this first line segment. What is the average of the x coordinates? What's the average of 1 and 12? Well, it's 6.5. Nothing to it. What is the change in y? How much does y increase from 1 to 6? As we move along that purple path, again, in the appropriate direction, well, y changes by +5. Well, on that line segment then, integral x dy, you just multiply those. You get 65/2. See how that's really, really simple arithmetic, right? The average of the x coordinates times the change in the y coordinates, multiply. Now you got to repeat for each one of these line segments. And so yes, okay, there is some arithmetic involved in this, because there's, what do we got, a total of 9 different line segments here. And okay, you got to, but it's easy arithmetic each time. You can totally do this. So just kind of at a glance, I did all this without a calculator, and I did have to a couple places. Okay, wait a second. I've got a 2-digit number plus another 2-digit number. Oh my gosh, what is that? But it's not that bad. It's very doable, and out comes your answer. And the area of this thing is 19. Much nicer than chopping this thing up into a bunch of triangles and trying to deal with each one individually, because they're bad triangles. Everybody with me? Okay. So this is going to seem like a shift of gears. And it's going to turn out that this is actually going to end up being another application of Green's theorem, but that's foreshadowing. So let's take this as a shift of gears, and we're going to consider this new thing. Y'all remember we've talked about this thing called flux. Remember, the idea of flux is if you've got a piece of surface, like an area, right? And if there's a fluid flowing through it, and if you want to measure how much fluid is flowing through this surface, like maybe the surface is like a screen door, and there's wind blowing through it. And if you want to keep track of how many cubic feet of air per minute are going through my screen door, something like that, right? And so flux, we developed back in chapter 3, I want to say, is a way of quantifying how much fluid is flowing through a surface. So here we're going to talk about what's morally the same idea, just in 2 dimensions. So flux through a curve. So forget about the 3-dimensional world. Just think about a fluid flowing along a surface, like maybe we're talking about groundwater, right, on the surface of the earth, or migration patterns of wildebeests, right? Effectively think of those as being kind of 2-dimensional. Right? The corresponding idea is, given a piece of curve, not surface, now just a curve. If we've got a flow of some sort, how much of the fluid represented by that vector field is passing through that curve? And I'm not going to redo the calculation like we did before. I'm just going to say the answer is it's exactly analogous to the result we had before. Namely, you got to look at the unit normal vector here. And let's see here, flow field dot unit normal times the length of the piece of curve that you're interested in. And if you flip back to the earlier notes where we were talking about flux through a surface, I think you'll find this is morally identical. It's just length instead of area. Okay, that seemed kind of believable. Okay. Well, we could talk about then, given that we had this idea of flux, we could talk about a flux through a special kind of curve, namely a boundary curve. And so let's imagine now that we've got a curve kind of going along like, anyway, I didn't give myself enough space here, but some curve that's actually a boundary, let's say. Right? And suppose I want to know the flux through that entire boundary. Let's take a quick moment to recognize why we would be interested in such a thing. Flux through a boundary. Flux represents how much fluid is flowing through. Why would I want to know how much fluid is flowing through a boundary? Well, because if this boundary is, let's say, for example, some, I don't know, a national border or something like that, and you've got wildebeests that are, flowing along, right, in their migratory pattern. Flux represents wildebeests leaving this region, right? Positive flux, that is, right? When this dot product here is positive, that means exiting the region. Whereas if the dot product were negative, such as if it was like this, right? And there's our unit normal vector. Negative would mean there's flow into the region. So the total around the entire boundary, the total boundary flux is a way of measuring how much stuff is entering or leaving your region. And so again, it's a total rate of change of stuff. And so very naturally an interesting thing. Does that make sense to everybody? Okay. All right. So how are we going to compute this? And it's a little bit of a tricky idea. First, a quick observation. This is just a clever observation. Where this is going to come up will reveal itself in a moment. But I know I'm interested in this integral f dot n, right? Let's go back up to here. F dot n is what I need in order to talk about flux. So f dot n. Okay. I'm going to take each one of these vectors and rotate a quarter turn counterclockwise. When I do that, it doesn't change the dot product, right? I mean, this dot that and this dot that are the same thing, right? I mean, keep in mind, dot product is computed in terms of magnitudes and the angle in between. So the dot product between my two fingers here, each finger has a magnitude, there's an angle between them. If I rotate them both the same amount, the lengths don't change, the angle in between them doesn't change, the dot product doesn't change. Yeah. So these two dot products are the same. And when you take a normal vector, specifically the outward normal, when you rotate a quarter turn counterclockwise, notice you get a tangent vector. But furthermore, because this is an outward normal, it follows further that this is the tangent vector such that the region is on my left as I go that way, right? So conveniently, this outward unit normal rotates exactly into my orientation, my boundary orientation unit tangent vector. Okay. And by the way, how do you rotate something by 90 degrees? This is a linear algebra thing. So we talked about this earlier in the semester, but also it's just a refresher from Math 218. rotations are a linear transformation, which means you can do it with a matrix, and it's an easy matrix to write down. And as it turns out, a 90-degree rotation, punchline is this. So that's another one that I want to make sure everybody realizes this is something you want to make sure that you can do. If you're a little shaky on, wait a minute, how did this rotation come about? Come to office hours. I'll be happy to show you. Big ideas from linear algebra. Okay. So let's compute total flux. The total flux through the entire boundary. Well, we're going to chop up the boundary into little pieces and chop it up, add it up, as we always do. Right? How would I compute d phi if I'm looking at a little piece of boundary curve, let's say between there and there, that little piece of boundary curve? How would I compute flux through that little piece of boundary curve? Well, I know the vector field. I have the normal vector. This little piece has size, let's say ds, and grand total then, the flux f dot n ds. This is just the idea from the previous page. Flux is the relevant component of the vector field times the length of the piece of curve. Cool. Yeah.
That picture is all contained in one plane, right?
Yeah. We're entirely in R2. For everything about Green's theorem is all entirely contained in R2. Yep. Okay. All right, and at a glance, it looks like we've hit a dead end because we don't know how to compute this thing, right? I mean, the integral f dot n ds, we've never seen that before. We don't have any formulas that, how to, I don't know how to compute n when I have a parameterization. Right? We don't have anything to do there. But here's where this observation kicks in. The f dot n is this f perp dot t. Because that turns that red integral into this blue integral, and this blue integral we do know how to compute because TDS is dx, and so we've got ourselves our good old-fashioned regular old vector line integral dot dx, integral of a vector field dot dx. So real slick move. That's why we did this observation here about rotating 90 degrees, is that's what allows us to turn the red bad integral that we don't recognize into this blue integral that's highly familiar and we know all about it. We're real good at computing it. Okay, so we could parameterize and et cetera here, but the better idea is to let's use Green's theorem. When you have a boundary line integral, this is a boundary after all. You just turn it into a double integral of Green's operator. We have to compute Green's operator here now. How do we compute Green's? Okay, well, remember Green's operator is, let's see here. Green's operator is an x partial minus a y partial. And let's be careful about this. It's the x partial. I mean, people get accustomed to saying dq dx minus dp dy, right? But really what it is it's the x partial of the second component of the vector field. The second component of f perp is p. And then minus the y partial of the first component of the vector field. The first component is minus q. Yeah, everybody good? So ultimately, it's just the standard formula for Green's operator, rotation, curl, whatever you want to call it. Now it's all over with the shouting. These minuses cancel with each other. So we have dp dx plus dq dy. And you may recall that from chapter 3, that is our old formula for this thing called divergence. So all together, remember at the very start of this calculation, way back at the beginning, we're computing flux. And what we see here is that I can compute boundary flux with a double integral. And this is called the divergence theorem. This is the two-dimensional version of the divergence theorem. There's a three-dimensional version that we're going to talk about later. Thus the qualification two-dimensional. Yeah, there you go. I'll also point out this is sometimes referred to as a version, maybe the flux version, you might say, of Green's theorem, because notice Green's theorem is where the big, that's where the magic happened, right? I mean, everything that happened before the Green's theorem step was just kind of set up, right? And everything that happened after the Green's theorem was just kind of simplification, right? Ultimately, this kind of is a variation of Green's theorem. So it goes by that name as well, the flux version of Green's theorem. Okay, all righty. Okay, so let's do one. So I've got a vector field here representing the flow of some sort of a fluid or the migratory pattern of a certain kind of bird or whatever. We got a vector field representing the flow of a two-dimensional fluid. Water flowing across a planes, whatever. And I want to compute the flux of this vector field, specifically this is the outward-oriented boundary flux, and the curve is the unit circle. So I said differently, I'm interested in the unit circle in the plane, and I've got this fluid flowing kind of all over every which way, and grand total, I know that in some places the fluid is flowing into the unit circles, and some places it's flowing out of the unit circle. Okay, yeah, but grand total, is there a lot of fluid flowing in? Is there more going in than out? Or net, right? The grand total, how much fluid is flowing into or out of this region and which way? So flux is what computes that. And we compute that flux with the formula above. All right, the formula above says that flux is a double integral of the divergence of your vector field. So here we go. Double integral of the divergence of the vector field. Now it's just kind of a matter of plugging things in. And oh my gosh, did I again get a sign? How did I mess up the sign again? Wow. Okay, this is I must have been in a rush when I did this. But anyway, so divergence, so we take the x partial of that and then the y partial of that. 2 minus 5 is -3, not 3. Silly me, I'll get this fixed as well. So -3 there. So the answer is -3 pi. Is that good? Everybody happy? Okay. All righty. So I want to give you all a different point of view on this. I think this is really valuable. Y'all know I'm a big fan of this point of view of accumulation and the corresponding notion of density, right? You can think of Green's theorem as being a statement about how boundary circulation is an accumulating quantity and there's an associated density. And this is really just to chop it up, add it up, just like if you're computing mass or something like that. Well, boundary flux also is an accumulating quantity, and you can see it entirely from that point of view, independent of Green's theorem. I claim boundary flux accumulates, and here's the picture justifying it. If we look at this left region, on that left region, what I have in light gray is the outward-oriented boundary flux. On this right region, what I have in dark gray is the outward-oriented boundary flux, right? So here I have drawn the outward-oriented boundary fluxes of two separate regions. And now let's ask, what is the outward-oriented boundary flux of the whole? The outward oriented boundary flux of the hole is this. Whoops. Does light gray plus dark gray add up to the blue? Well, there is the annoying matter of this edge here, but you notice that this edge appears twice, but with opposite orientations, and so they cancel. So, you know, oriented that way as part of the part of the boundary of D1, oriented this other way as part of the boundary of D2. And when you add up those two line integrals, they cancel. It's they're same curve, opposite orientations. You get the exact same magnitude with the exact opposite of signs, so they cancel. What do you think? Everybody see how this works? Okay. So those canceling, we are left with exactly what we're supposed to. So boundary flux being an accumulating quantity, you can talk about its corresponding notion of density, and we already know what the answer is, so I'm just going to skip down to that. Here's the theorem we previously wrote down. Flux is a double integral of divergence. And now just to put it into context, let me remind you, we have this formula for computing masses, and the integrand, we call it mass density because it literally tells you mass per unit, little bit of mass per little bit of area as it accumulates. And well, likewise, here's our theorem about circulation, and Green's operator we call circulation density, because we're computing circulation. And because Green's operator is the thing that tells you how much of that accumulating circulation you get per unit area. Just like with mass density. I mean, the motivation for the term density is exactly the same. And then same story here. And again, I like to write them sort of, in sequence here so you can see the analogy. I mean, it's the same thing. Here, flux is an accumulating quantity. Little bits of flux relate to little bits of area like this. In other words, divergence is what gives you flux per unit area. Divergence, therefore, is flux density. Cool. So what's nice is then that this point of view on the two-dimensional divergence theorem, this point of view does not require citing Green's theorem. I just said, well, it's analogous to Green's theorem, but this, you can think of this as, the notion of accumulation combined with the corresponding notion of density. Yeah, there's details of a calculation that you have to do there. It's a bunch of algebra. Let's not worry about it. Same kind of derivation we did before. Okay. All right. Is everybody happy? Okay. I know that this is kind of mysterious and sort of like head scratcher that, mass density is something kind of visceral in the sense that we can see and feel and experience mass and density. And we've all felt like, oh, that oddly heavy rock that must have a lot of iron ore in it or something like that, right? As opposed to the volcanic rock. Oh, wow, how light. It's the same size, but it weighs a lot less. I mean, you can really kind of get your hands on literally and have an intuition for that. And these ideas here are a little abstract and kind of mysterious. I'm going to point out another example that you've already seen and you already believe and that we can draw easy pictures of. That is likewise, same thing, just a matter of accumulation and density. And it's a point of view you probably haven't seen before, but it's the fundamental theorem of calculus. Really deep down, fundamental theorem of calculus is a statement about accumulations and densities. So in particular, do I have time for this? You know what? I have 35 seconds on a Friday. I better not start with this. Let's draw the line right here. We will pick up with this on Monday. So yeah, see y'all later. Have a good day.